Hello, everyone, and welcome to today's webinar. My name is Jovana Mitrovic, and I'm R&D chemist at Silk Technologies. Today, we will be discussing a topic that's becoming increasingly important in modern bioanalysis, oligonucleotide analysis. And I'll share some of the innovative solutions we have developed for their characterization and separation. So we will go beyond traditional LC principles to understand why oligonucleotides are so challenging to analyze and how we can overcome those limitations using our bridge ion separation technology, or BIST. So let's start by taking a look at agenda for today's session. Before we dive into the technical part, let me just give you a quick overview of today's agenda. We'll start by looking at the chemical nature of oligonucleotides and understanding what makes them so difficult to analyze by liquid chromatography, especially compared to small molecules. Then we'll explore the types of interactions that influence their retention and selectivity. Things like electrostatic forces, hydrogen bonding, and metal coordination effects. After that, I'll introduce bridge ion separation technology, or BIST, which is a unique approach developed at Silk to control these ionic interactions and achieve better separation performance. We'll then move into practical part, showing how BIST can be applied for oligonucleotide analysis, how retention depends on charge, sequence, and structure, with real chromatographic examples. So by the end of the session, you'll see how BIST and our specialized columns can simplify the analysis of negatively charged biomolecules. So let's begin by addressing a key question. Why are oligonucleotides so difficult to analyze by liquid chromatography? Oligonucleotides are highly negatively charged because of their phosphate backbone. These charges cause strong electrostatic interactions with metallic surfaces inside LC systems, such as column hardware, ferrites, or even tubing. So as a result, analytes can adsorb onto metal surfaces, leading to poor recovery, tailing peaks, and signal instability. In addition, ionic interactions tend to dominate the retention mechanism, which often masks the subtle selectivity we would normally expect from hydrophobic or polar interactions. So these analytes as well are prone to carry over between injections, making reproducibility and quantitation especially challenging. So in summary, strong ionic interactions, metal adsorption, sometimes even detection difficulties are the main reason why conventional LC often fails for this type of analytes. So now let's take a closer look at what gives oligonucleotides their chemical personality. They're composed of repeating phosphate sugar base units. The phosphate groups are negatively charged, and the bases such as adenine, thymine, guanine, cytosine, or uracil introduce pi-pi interactions, polar and weak hydrophobic interactions. Because of this complex nature, oligonucleotides are strongly ionic, but also have other properties making them difficult molecules for their analysis. Their retention in chromatography depends on sequence length, base composition, and modifications. For instance, a longer or more GC-rich oligo will typically retain more. However, this complex structure also increases the likelihood of secondary interactions, especially hydrogen bonding and coordination with metals, which can severely affect peak shape and recovery. So when we design a chromatographic system for oligos, we need to balance ionic, hydrophobic and polar interactions while minimizing unwanted surface effects. Here we can see the main types of interactions that occur between oligonucleotides and chromatographic systems. Ionic interactions. This is the most dominant type, driven by electrostatic attraction or repulsions between charged groups on the non-analyte and stationary phase. Hydrophobic interactions. These play a smaller role because oligonucleotides are not very hydrophobic, but bases can still interact weakly with non-polar surfaces. Hydrogen bonding and dipole-dipole interactions. These happen between nucleobases and polar surface groups, adding just another layer of complexity. Metal surface coordination. These are critical. Phosphate groups can coordinate with exposed stainless steel sites, leading to irreversible adsorption or sample loss. And finally, we have steric effects, because these are large molecules. Pore accessibility and molecular folding can influence how deeply they penetrate the stationary phase. So when all these interactions combine, you can imagine how complicated the retention mechanism becomes. Now that we understand the problem, so let's talk about solution, or BIST. Bridge ion separation technology was developed by Silk to address the exact challenges we've been discussing. The idea is to create a controlled ionic bridge that connects the stationary phase and the analyte through doubly charged ions in a mobile phase. This approach allows us to fine-tune electrostatic attraction, so we can actually use ionic interactions to our advantage rather than fighting against them, while in the same time minimizing unwanted interactions for these large multi-charge molecules. So the idea is to have a simple solution for analyzing complex multi-charge molecules, minimizing unwanted effects while still having the ability to have highly selective solution to separate oligonucleotides with subtle differences. So by manipulating the charge balance and the solvent environment, this provides a new level of selectivity, especially for analytes that were previously inseparable or unstable on traditional single mode columns. So let's look at how these mechanisms work. The BIST mechanism relies on a bridge formed between the stationary phase and the analyte via doubly charged ions, such as, for example, magnesium. The stationary phase carries a fixed charge. So let's say it's negatively charged. The analyte, like oligonucleotide, is also negatively charged. So normally, these two would repel each other. But when we introduce a doubly charged cation, for example, magnesium, it binds simultaneously to both surfaces, forming a kind of ionic bridge. And this bridge stabilizes the interaction and controlling how strongly the analyte is retained on the column. Polar solvents, like water, solvate these ions, which helps controlling the bridge. Solvating the ions helps disrupting of the bridge. Therefore, by controlling the amount of water in the mobile phase, we can control the retention of the molecules. High organic content would promote the bridge formation and interaction of oligonucleotides with stationary phase. And by increasing water content, the bridge weakness and analyte elutes. So in short, the bridge acts as a controlled mediator, giving us both stability and selectivity for charged analytes. So there are three key rules that govern BIST separation. First, you need a high organic content in the mobile phase, such as acetonitrile. This reduces solvation and allows bridge to form more easily. Second, the double charge ionic modifiers, such as magnesia, or TMEDA must be present in the mobile phase. And third, the charge of the modifier must be opposite to that of both the stationary phase and the analyte. So when all three conditions are met, BIST becomes very effective and retention becomes predictable and tunable, which is crucial for separating complex biomolecules like oligonucleotides. So let's see how this works in practice. First, the retention is based on the number of charges. In this example, on the left, we analyzed oligonucleotides 8-mer and 37-mer using a cation exchange column, or BIST, with magnesium acetate buffer at pH 4. As you can see, retention increases with the number of charges. In other words, the longer the sequence, the stronger the interaction through the ionic bridge. And the retention is primarily controlled by the gradient of higher organic content to lower. Meaning, when we slowly increase the water content in the mobile phase, the water starts solvating ions, where molecules with less charges elute first, and molecules with more charges, such as 37-mer, will elute later when water content is higher and ions solvate more to reduce significantly electrostatic interactions. Example on the right shows analyzing 16-mer oligo with all T bases and with shorter sequences present as impurities. As you can see, due to unique BIST mechanism and gradient, we can separate impurities based on the length of sequence and number of charges they have. Therefore, even one charge difference is enough to separate similar oligos based only on the length. Additionally, as you can see, there is no tailing or very broad peaks for oligos, while mobile phase does not have high amounts of salt like in usual oligoanalysis. There is no need for column passivation. The analysis starts from the first injection. Why is that? Well, in traditional modes, interaction of oligos, especially longer ones with metal sites, column hardware, and frits, are very pronounced, and it usually requires passivating the column, high amounts of salt in mobile phases, etc. Here, all of that is overcome by having doubly charged positive ions in the mobile phase. Therefore, very chelating phosphate groups prefer interacting with doubly charged positive ions than metal sites, preventing this unwanted interaction, loss of signal, irreversible adsorption, and carryover. This predictable trend makes it much easier to separate oligonucleotides by length of degree of modification without need for ion pairing regions or extremely high salt concentrations. Let's look at the next example. We kept the same setup, a cation exchange column with a TMEDA-forming buffer, and look at how chain composition affects retention. Here, on the left, we can see that even oligonucleotides of the same length can have different retention times depending on their base composition and charge distribution. They mediate and modulate the electrostatic environment and accessibility of those inherent negative charges, impacting the oligo's overall charge distribution, stability, and behavior. Therefore, in this example, we can see how we can separate short 5-mer oligos that differ only by the base composition. Additionally, example on the right, we analyzed 17-mer oligonucleotide with MS-compatible conditions by using very low amount of buffer, only 1 millimole, in order to not suppress the signal while still have ionic modifier capable of bridge forming for BIST interaction. So this demonstrates that BIST doesn't just separate based on size or total charge, it also has the ability to distinguish the subtle differences in molecular structure, which is extremely valuable in oligo quality control and impurity profiling. While BIST offers a powerful solution for oligonucleotide analysis, we wanted to take that simplicity one step further. So we developed a dedicated column called OligoMG. OligoMG operates on the same foundational principle as BIST, ionic bridging, but with one key improvement. It completely eliminates the need to add any bridging ions into the mobile phase. Here is how it works. The stationary phase in the OligoMG is negatively charged, just like a standard negatively charged BIST column. However, the surface is preloaded with magnesium ions, which are doubly charged cations, and these magnesium ions serve as built-in bridging agents. So now when a negatively charged oligonucleotides enter the system, it no longer requires a separate ionic modifier in the mobile phase. Instead, it can immediately interact with the stationary phase via the pre-positioned magnesium bridges, enabling effective retention through the same B-style mechanism. The mobile phase becomes much simpler. All that's needed is a basic fodder and acetonitrile gradient, no buffers, no salt, and no pH adjustment. In this example, we show the separation of several negatively charged oligos of the same size using just the water acetonitrile gradient. The result is strong, selective retention and clean separation without any need for method reoptimization or complex mobile phase formulations. So by having the bridge-forming ion directly into the column, OligoMG streamlines the workflow, reduces method complexity, and brings the benefits of BIST to a broader range of users and labs. So one of the most powerful and unique advantages of BIST platform, including the OligoMG column, is the level of selectivity it provides when separating closely related oligonucleotide species. So let's break down what's happening. BIST-based interactions happen directly on the surface of the stationary phase via the ionic bridges. Because of this surface level, highly localized interaction, the system becomes extremely sensitive to subtle variations in the structure and properties of the analytes. This opens the door to a much more refined level of discrimination. So there are a few key ways this selectivity is expressed. One, molecular geometry. Even when oligonucleotides have the same sequence length and charge, differences in how the molecule is folded or structured in solution can influence how it interacts with the surface and the bridging ion. Next, charge density and distribution. It's not just about the number of negative charges, but where those charges are located and how strongly they're expressed. A slight variation in base composition or phosphate accessibility can influence retention behavior. Acid-base strength of functional groups. Some nucleobases are more basic than others. This influences how the phosphate backbone expresses its charge and therefore how strongly the oligo binds through the bridge. Structural isomerism. Oligos of the same length but different base arrangements, known as sequence isomers, can exhibit different retention due to spatial and electrostatic differences, which are captured effectively by the BIST mechanism. So, what does this mean practically? It means you can resolve not just the full-length target oligonucleotide, but also closely related impurities, including shorter sequences that result from incomplete synthesis, degradation products from chemical or enzymatic breakdown, minor structural variants or byproducts that differ by just a few nucleotides. So let's take a closer look at the two examples shown in this slide to illustrate how oligo-MG achieves high selectivity. In the example on the right, we are separating three different 18-mer oligonucleotides. These sequences are the same length and have the same number of negative charges, but they differ in their base composition, that is, the specific nucleotides making up the chain. Even though they're structurally similar, the oligo-MG column is able to resolve them using a straightforward gradient from 65 to 40% acetonitrile in mobile phase. And this shows that the retention is sensitive not just to size and charge, but also the sequence of specific differences, such as variations in base strength and distribution of charge along the chain. On the left, we see separation of 10A oligonucleotide, a sequence made of 10 adenines and its shorter byproducts, which can appear during synthesis. Despite the close similarity, the oligo-MG column resolves the full-length product from these shorter fragments using a gradient from 75% to 50% acetonitrile in mobile phase. No salt, no buffer, no any ionic modifier. So together, these examples highlight how BIST technology enables fine-tuned separation based on both structure and composition using a simple organic gradients. And this level of selectivity is especially useful for applications like synthesis monitoring, purity checks, and impurity profiling of oligonucleotides. And that brings us to the end of today's presentation. I hope this session gives you useful insights and ideas you can apply in your own analytical work. And if you have any questions, please feel free to reach out using our contact information here or visit our website. Thank you so much.